Good morning, college algebra. Happy rave day. As you can tell, I'm all festive with my rave stuff. Speaking of rave, this sponsor of today's video is sponsored by Rave Shadow Legends. We're so excited. Kermit, roll the ad clip after editing. Okay, so now let's talk about quadratics. Yesterday we kind of touched on the axis of symmetry, right? Where we have the x equals negative b over 2a. Yes, and that will always be with your vertex. Vertex being the max point or min point of a parabola. Now, of course, we know what quadratics look like, right? It's our best friend, right? Since day one, we went to preschool together. He invited us all to his Chuck E. Cheese parties and stuff. So this is kind of what a parabola would look like. And even better, this is what a parabola looks like if a, that number in front, speaking of which, there's two forms of parabolas we could graph in. One of them is your standard form, right? Standard form being ax squared plus bx plus c. And then the second form being vertex form, meaning you have a, and then in parentheses, x minus h quantity squared plus k. So that is the vertex form, meaning that's going to be associated with your vertex, which is hk. Remember, h being your horizontal, k being your vertical. And since it's a minus h, that means you're going right, plus k means go up. So considering this, your vertex form or standard form, this would be what a parabola kind of looks like if your a was positive, meaning the number up front's positive or just 1. However, if it's negative, it's going to look like that good old frowny face, right? And we don't like frowny faces here, but it does happen. And that's actually a more common quadratic you're going to come across in real life. Think about like a catapult, right? Or projectile motion. You shoot a catapult, gravity is quadratic, meaning that if you give the position y of t, it's going to be some sort of quadratic pointing down, right? That way you know where it lands. And we've used that example so many times at this point. So now, going in and doing a few examples, let's say we want to graph this awesome quadratic. Let's start off with the vertex form, right? So you have f of x is, let's put a to be just 1. So x plus 2 squared minus 4. How would we graph that? Well, let's do it. Let's get it. This is associating our vertex where we are starting, actually, since that's a plus inside, if you want, you could rewrite it as x minus negative 2 to kind of see the difference here, minus 4. So we're going left 4, and then we're going to go down 4, or left 2, down 4, my bad. So starting at the origin, left 2, down 4, and it's going to be pointing up. And if you remember the perfect squares trick, right? The perfect squares trick being from the vertex, so the starting point. You can go over 1, up 1, and then over 2 from the vertex, down up 4. And if you really want to, you can go above and beyond, and then go over 3 from the vertex, up 9 all the way up here. And since the vertex is always located with the axis of symmetry, that means it is going to be reflected. It's symmetric about this axis of symmetry, so that means you could go left 1, up 1 as well. So this is going to perfectly match, because that's the origin or the nature of quadratics. Now, obviously, this is just a rough sketch, so we don't have to worry too much about it. Let's go with a more spicier example, right? Let's say that we don't have an vertex form, and you want to just kind of still graph it, because why not? So let's use another example. Let's say, hopefully this is a good example. If not, then it's going to be a gross example, but yeah. Negative 2x squared plus 8x minus 10. So let's use that good old standard form. Now, if you remember all the way back when we graphed in standard form, we had to find the axis of symmetry first, and then plug it into original function to find the vertex. So that's why vertex form is much more convenient to graph in. So let's do x is negative b, so negative 8, over 2 times a, 2a, 2 times negative 2. So when you do that, you have x equals positive 2. Now to figure out where to start, where our vertex is going to be, we plug this in to our original equation. So f of 2 is negative 2 squared, and then order of opposite our way to victory, minus 10. So then we have 4 times negative 2 is negative 8, plus 16 minus 10. Oh, this is going to be beautiful. Hang on. 8 minus 10. Oh, negative 2. Okay, it's not that obnoxious. Sweet. All right, so our vertex is 2, negative 2. That's our starting point. So let's graph it, why don't we? Just be like a staring graph it. By the way, let's do our first question of the day. While I'm trying to graph this, let me think of a good one. What is your favorite snow activity? It could be like sledding, making snowmen, snowball fights, you know, the whole 9 yards, and or snow angels if you really want to. And why would that be your favorite snow activity? It could be just a personal reason. It could just be that it's fun, or because, you know, it's a tradition kind of deal. So that would be question number 1. So make sure you put that there. And then let's finish off this graph, and I'll think of another question 2, which has to be mathy because mathematical. So now I'm graphing. So 2, negative 2, that's our starting point. And it looks like it's pointing down. So that means that we're going to be going right 1, down 1, but we have that 2 hanging out front of our A, right? So it's going to be over 1, down 1 times 2. So we're going to have to go down 2 now. And from the vertex, using our little perfect squares trick, because the 2 out front, because A is that number right there, instead of going over 2, down 4 from the vertex, it'll be over 2, down 8, or down 4 times 2. So all the way down yonder. And we kind of already expected that because it's going to be skinnier. It'll be a vertical stretch with all that transformation stuff we did. We just took a test on, right? Kind of know how transformations are going to go. So that negative tells us reflect over y. This tells you vertical stretch, making it skinnier. But now that we are in the quadratics unit, we have to be a little bit more precise. So let's actually, I think I got a good question 2 example. Let me think of one though. But I think since this is actually applicable stuff, let's go a whole 9 yards and actually do kind of a little word example. So typically the way we're actually going to be using this, and if you're actually going to use it outside of college algebra, it's going to be in this form more or less. So let's say you got negative. Well, first let me just do the original equations and then kind of make some numbers up. So in physics or any physical science classes, the very first thing you learn actually in physics. So, and most of you might be taking a physics class at some point in your life. But this is your height function, y being your height and t being time, right? So let's say that you're kind of on a cliff right now. H sub naught is going to be your initial height. So that little sub-zero, we call it naught, just because like a null and, you know. So that's your initial height, right? Vi, that's going to be your initial velocity, meaning how hard you throw your first thing in the y direction, which typically you have to use trig to kind of find the y direction, but just for our intents and purposes, yeah. And then g is your gravity, so negative 9.8 meters per second, right? Or meters per second squared, since it's acceleration. That's a meter per second, that's a meter, so they all kind of cancel and make the same units. Anyway, let's say you're just chilling with your friend on a cliff, right? And you want to throw some sort of baseball, and we want to see how long it's going to be in the air or when it's going to be hitting its max. When it's going to hit its max, you could just use the axis of symmetry, right? And whenever you're figuring out where it's going to be hitting the ground, you have to use the set this equal to 0 into the quadratic formula. So I guess your question 2 would be, when is it going to hit its maximum height? And what will that maximum height be? So you use your axis of symmetry formula and plug it back in. Do some crazy stuff with your variables. I know it's going to be obnoxious. Hopefully it cleans up nicely, but I'll also do it too because I have to check the answer anyway. So that'll be question 2, is considering this situation, when would the maximum height come? And what would the maximum height be in terms of variables? So there we go. Anyway, happy Rave Day. Hope you're also celebrating too. So, and I know Kermit's going to be Mr. Spartan now because there's no other competition. I'm just looking at him. Yeah. So, happy second AMI day. Enjoy your 5-day-ish weekend. So, yay.